Okay, so just before we start, a couple of useful links for undergraduate students who are on the line. You can go to any of these websites for more information about various outreach opportunities at the various institutions that are participating in our science center. If you have any questions, you should feel free to email any of the people on this email list. And if you go to the top link here, this URL, you'll find all of this information and the emails that you can, the email addresses that you can send questions to. Just before we start, rules of the road are very simple. We'll have a Q&A panel after the panel discussion at 4:30. So we'll go for about half an hour and then open the floor for questions. You're all muted except for the panelists and the hosts. So if you want to ask a question, raise your hand. Or alternatively, just type your question in the chat box and the moderators will ask it for you. So without further ado, Alexandra, it's all yours.
All right, thank you, Dr. Merkin. We're so excited to have everyone here with us today. Hopefully you'll learn a bit, not just about the really cool science that's being done through the Center for Geospace Storms, but also about some of the people that are doing the science and the ways that they've been able to build their careers to the cool places they are now in their career. So I'm going to go through some questions. This will be a moderated panel, and I will ask the questions of each scientist, and we'll just start with the first one, and they'll both have a turn answering that question, and then we'll go to the next one. So Dr. Sarah Vines, we'll start with you. Are you ready to answer the first question?
Yeah, I hope so. Yeah.
Awesome, great. So I'll ask you first, and then I'll go to Anthony and ask him that first question for you. So describe your career path and what inspired you to pursue your scientific career.
Yeah, so if you ask this to a lot of us in our field, I think what you'll find is that it typically is one that is meandered over time. So I came up at regular public high school. I grew up in North Carolina, and I knew from a very young age that I was interested in something more in the science fields. For a long time when I was young, though, I was like, I'm going to do dinosaurs and I'm going to do anthropology. And then at some point it transformed into a real interest in math and physics. I think when I actually went to undergrad, so I went to undergrad at the Florida Institute of Technology, and it, I think, was still with a really open thing of exploration and not quite sure exactly where I wanted to go, but knowing that I wanted to do something in space science. It also helped that it was warm and at a beach. So when I went to Florida Tech, I actually was in one of the earliest iterations of a bachelor's degree program they had of astrobiology. And so what ended up happening is I took like half of my time in molecular biology, organic chemistry, and the other half of it was in astrophysics. So I got to learn a lot about a lot during that time. From there, I actually went to grad school at the University of Texas, San Antonio, to be in their joint program they have with the Southwest Research Institute to do space physics and space physics instrumentation. And it was that last part that really was the draw that got me there. It wasn't just doing the data analysis of all of the measurements being returned from NASA satellite missions. It was also actually, building and testing the hardware, the sensors that go on those spacecraft missions. So I went to there, got my PhD in physics, and that was in 2016. But my dissertation was about space physics, specifically Earth's magnetosphere. And then from there, I actually took a postdoc position at the Applied Physics Lab and I've stayed on since then. So I've kind of wandered away from planetary science and astrobiology, and now I'm like hardcore Earth magnetospheric physics and space physics. Yeah.
Awesome, thanks. Anthony, same question to you. Describe your career path and what inspired you to pursue your scientific career.
Yeah, so I've always been interested in space and science, of course, since I was a little kid. In high school, I actually got into programming just through the couple courses they had there. And so when I applied to undergraduate programs, I applied as a computer science major, and then realized in there with my last semester of high school that I enjoyed physics as well, and I could actually do the physics and some of the interesting stuff. And so I switched over to physics in undergrad and enjoyed that. I went to Old Dominion University, which was, they're more of like a particle physics school. They're really close to Lawrence Livermore, the accelerator facility. So I did some work with that. But then actually, for some reason, I guess, space always seemed really cool, but something that was like out of reach, not only literally, but as a career for some reason. But then I got involved in undergrad in an organization called Students for the Exploration and Development of Space. And that's when I realized like, oh, people like actually have jobs in this field that are, maybe accessible to me too. And then over my last couple of years of undergrad, I was looking more into space physics. And then I got into plasma physics, and just looking at graduate schools I could go to. I landed at Rice University, where my project that I'm still working on is doing computer models of Earth magnetosphere, but sort of applying what we know about Earth's magnetosphere and its interaction with the solar wind to exoplanets, and trying to understand exoplanet environments. And so that's kind of where I'm at now.
Great. Well, you were starting to get into your science, and that's actually the next question. And we'll start with Dr. Sarah Vines first. So a couple of questions about the work that you're doing, why it's important, why it should be, why people in our community should care about it. And if you have a slide or two you want to share, you can do that now. Awesome that you're shaking your head that you do. And also to make sure that you also mention how you're using spacecraft data in your research as well. So go ahead, thanks.
Okay, yeah, I'm gonna just share a few slides and hopefully try to keep it brief, but please, if I'm going on too long, don't be, cut in. So if I may share this. So first, one thing about why you should care is that it's really fun working with missions and mission data, especially when you start from the ground up. So I actually got to go, this middle photo here is actually me at the launch of the magnetospheric multiscale mission. It was the day before it actually launched. I got to be there in person for that, which was incredible, because that was my thesis work, the crux of it. And then the one on the far right is actually, we got to see the Parker Solar Probe when it was still at the Goddard Space Flight Center before it was delivered to Florida for its launch. So launches are a really nice perk. The one on the far left was actually an summer school program that I did in graduate school, where we ended up at JPL to do spacecraft mission design planning. So this is a mock-up of the Curiosity rover that we got to see and play with. Okay, so just real quick, so what I actually work on is a lot of NASA satellite mission data. And so really what we do is, my primary focus is that solar winds, that upstream solar wind and interplanetary magnetic field that permeates the solar systems around us, that interaction with the Earth's magnetosphere, both at the front side here, where they first meet, and also really at these kind of polar cap high latitude areas really close to the Earth. But what I wanted to show here is that there's a lot out there. And so I've worked with a tidbit of a little bit of everything that that NASA has actually put up, and some other things through NSF. So it's been really neat. It's been a lot of interesting data sets to work with. One of the main things though is MMS, and what that one does is it studies a lot of aspects of magnetospheric dynamics and plasma processes, but particularly it studies the phenomenon of magnetic reconnection, and that's what I cut my teeth on and I'm still interested in. So I'm just showing here just a sketch of what that looks like. And really what I've gotten to do with MMS in particular is actually have aspects in the low energy ion detectors, but what I'm showing here is an animation of the magnetic field measurements. And that is actually what I'm a part of now, is the Fluxgate magnetometer instrument team. And so what we can do here is look at boundaries, look at dynamics. Here we are actually going through a reconnection region at the upstream dayside magnetopause boundary, so which has been really, really cool. But one of the other big aspects for me that I work on in this solar wind magnetosphere coupling is then what happens down to the Earth's ionosphere and then down into the atmosphere. And from that, again, it's through magnetic fields. So what my other major project is Ampere. And what it basically is we take all of the magnetic field data from the Iridium communications satellites. So everything from this network, we actually back out the magnetic field data because they carry magnetometers on board for their avionics. And then from there, we actually can pull out these major electric current systems that close in this polar cap region of Earth's ionosphere. And so from that, why that matters is that what's happening in that polar cap region is, on one hand, a manifestation of what's happening in the magnetosphere in response to the solar wind, and on the other hand, a driver of ionospheric and atmospheric dynamics. And the atmosphere and ionosphere also affect these current systems that we're seeing. So really, this is kind of that intersection point. And so when we think of space weather and we think of geomagnetic storms, what we're really talking about too are these kinds of really dynamic, strong responses. So what I'm showing actually is a storm time, and we can see the magnetic field vectors going nuts, and then there's a field line currents on the far right from that, and just basically how dynamic that is and how that can actually really affect a lot of things downstream in the ionosphere and atmosphere. Yeah, so that is kind of the major crux of what I do, is try to understand the plasma processes of dynamics right now, primarily through magnetic field and current observations.
Awesome. And people might have questions, so remember those questions and we'll get them answered after we're done with this panel discussion. So thank you so much, Sarah. And Anthony, same question to you. What explain some of your research and why it's important and how you use satellite data to do your research?
Oh, well, I don't use satellite data at all, actually.
Oh, okay.
So I use telescope data a little bit. Right, so essentially, like I said earlier, we are taking what we know about Earth's magnetosphere and also a bit of Jupiter and all that, and applying it to exoplanets. Because right now, the way that we know about exoplanets is we detect them either due to the wobbling of the star or through the planet passing in front of the star. And from that, we get like the distances from the star, the mass and size of it. But really beyond that, we don't really have any observational data we can use very much. So we have, plenty of satellites around our magnetosphere, and we don't have any of that in for exoplanets, unfortunately. But at the same time, we think that in terms of habitability, understanding the magnetic field is very important. And so what we do is we try and bridge that gap of knowledge with models. And so just to give you a sort of sense of scale is, so this is for Earth. And so the sort of balance between Earth's magnetic field and the solar wind usually extends to about 10 Earth radii. But for a lot of exoplanets, they're much closer to their stars. And so this is a simulation we did at Proxima b, our closest neighbor planet. And based on current best estimates, this boundary that's at 10 RE here is actually right down at the surface here. So that has some pretty serious implications for atmospheric loss and any life that might evolve on that planet. And the other tricky part is, like I said, we don't really have any way to confirm this observationally right now. But I'll come back to this in a second. We know that Jupiter and actually all of the solar system, magnetized solar system planets produce radio emission. And there are some people that that predict that we should be able to see this emission from exoplanets, and yet we have not yet. So we use these large-scale arrays here to look for radio emission from other planets. We haven't found them yet, even though, based on what we know about our own planets back here, we should be able to see at least some emission from exoplanets. So one of the questions is, so why don't we? And so that's kind of what we are looking into as well. And so part of that is, this is part of the modeling suite that I've been using, developed primarily by Johns Hopkins in their collaboration with CGS. And so this is a pretty low time resolution video, but what we're interested in here, we're driving the whole system. This is a little bit strong, but we're interested in what shows up in the ionosphere, because that's where this radio emission is produced. And so we're working on trying to quantify that and try and explain why these radio observers haven't been able to see this emission. So it's kind of a work in progress, but it's very new and interesting. And yeah, so that's pretty much what I do, why I think it's important. Also, once we do detect the magnetic fields, that tells us many other aspects about planetary evolution, like if they have internal dynamos to drive those, that tells you about how the planet evolved. And also gives us a whole bunch of reference points for where our own solar system planets sit in the grand scheme of all the planets in the galaxy.
Great, thank you so much. All right, so our final question is basically, what, I'm going to actually add a little bit to it. What experiences did you take advantage of when you were an undergraduate that helped you get on this path? And what opportunities are out there right now for undergraduates that you think they could take advantage of if they want to get more involved in this work? So Dr. Sarah Vitens, we'll start with you.
Yeah, sure. So one of the huge things for me, my junior year, I actually was a part of the USRP, which is the Undergraduate Research Internship Program. Yes, sorry, I was trying to remember the acronyms. And so at that time, so they had basically two iterations of this, one that was a summer session and one that was a semester-long session. And so I actually took off a semester to do this program. So I went out to NASA Ames, and I worked with folks in one of the departments at Ames doing actually ancient Mars global climate modeling. So if any of those kinds of research internships through NASA, through NSF, through other programs like in universities, that is a huge thing to take advantage of, because it can get you exposed to other scientists, actually exposed to the work that and what a workday actually looks like. For me, that's where I learned how to program. Before that, I really didn't do that much at all. And so that was kind of really where I learned how to actually do this kind of data analysis. And I got to meet a lot of other people from across the country, and a lot of other like working scientists in all these different environments. So that was pretty pivotal. Yeah, I think that was one of the main things for, I will say, if you do see things that you're like interested in as far as graduate programs, anytime any of those universities are doing prospective student days or any other information sessions, I would definitely go ahead and take advantage of that. Along with the department and the kind of program you're interested in. Sometimes you can't really know if it's going to be a good fit until you actually go there and ask the current students questions. So anytime there are things like that, I would say absolutely take advantage of it and do some research beforehand on these programs if you're able to.
Great advice, thank you. And same question to you, Anthony. What opportunities did you take advantage of as an undergrad, and what opportunities would you suggest today's undergraduates take advantage of?
Yeah, definitely support just trying to get involved in either the groups currently at your campus or applying to these external programs. For me, like I said at the time, I wasn't really doing any space physics at that point, but I was still involved in, our department was building one of the main chambers for the particle accelerator. And so I got involved in that, both sort of in the clean room and also doing some modeling for them. So I guess for programming wise, it doesn't necessarily need to be in exactly what you'd hope to do later on. Just any sort of programming expertise carries over pretty well to other fields, for sure. So that's kind of what I was involved with in undergrad. But actually, So of course, a lot of programs exist for undergraduates as well, but I got to go to NASA Ames my first summer in graduate school, and that was a real big, really important experience to get involved and see what else is going on. So as far as undergrad students getting involved now, yeah, I would just say in general, feel free to reach out to anyone in your department doing something interesting. Or right now we have an undergrad working with us as well, running the model and exploring all the different parameters and all that. So even if it's at another university, I'm sure they'd be very interested to have a very ambitious student want to work with them.
Awesome, thank you. Yeah, I'll just say for me as an undergrad, a great experience I had was actually working alongside graduate students and asking them if they had any work that I could get involved in. And they were always like, yeah, you could do something for me, here you go. So even if it, that's the easiest way to start, that networking, just take advantage of this graduate students that are already there in your department. So thank you so much, everyone. So we're going to go ahead and open it up to questions right now. There's a couple ways we can do this. You can either type your question in the chat window and I can read it, or if you would like to ask it yourself, just put in the chat window that you have a question and we'll call on you and give you an opportunity. And you can ask either of our panelists questions. So go ahead. Anyone want to start?
So I actually have a question. The question is for Anthony. Can you talk about what do we know about exoplanets? How do we observe them, and what do we know?
Yeah, so again, as far as things that we know for sure, really comes down to we know their planetary radius, some of them, not all of them, but ones that pass in front of their star, we can see how much light is blocked and therefore figure out their size. The mass of the planets that we detected, we have a pretty good range on them. There are sometimes when the planet passes in front of the star, it'll actually not only include the visible light, but the emission from certain spectral lines from the star, and then you can get some information about the atmosphere, some very preliminary information about the atmosphere. And then hopefully, I think they finally announced that they're going to send up the James Webb Space Telescope in the next year or something like that, and that's specifically purposed to look for at exoplanetary atmospheres. So we'll get a lot of actual direct information about that pretty soon. And everything else is kind of indirect or based on models or statistics and all that. Like for example, Proxima b, we don't actually know its size for sure, but based on the conditions of the stellar system and all the other planets that we do know the radius of, they predict it to be about 1.3 Earth radii. And so that's all we really know on paper right now. And yet people are still able to run a lot of simulations, make lots of predictions on what these systems look like. But also part of the work we're doing is because our observational capabilities are so low, part of the work is to actually sort of estimate what observables you could look for and set a sort of sensitivity threshold for future observations. So it kind of helps give that a benchmark.
Cool. Thank you.
Yeah.
And there's let's see, there's a question in the chat from Colton for Dr. Vines. Are you looking at getting data from satellite mega constellations like Starlink or Kuiper? Would that be beneficial to your research, like an expanded version of the Iridium data you mentioned earlier?
Yeah, this is a conversation that's come up several times recently as, yes, Starlink's come up. We were having preliminary conversations with people like OneWeb to see what could be feasible. Honestly, the more that's up there, the better. It's kind of always my take on it. Because so if we can, so there's a lot of little intricacies and details. One of it, there's an interesting area you get into with working with private companies and what we can get from them and what we are able to share. So that kind of, which tends to run counter with what we do within science, which is make everything available. So there's some interesting things that we learned we had to work out to do this. But once that's all done, it's basically, okay, do they have good enough measurements? Because one thing that to keep in mind for trying to pull out these magnetic field signatures to get these currents is like the Earth's main field, the dipole component of the Earth's magnetic field, that close to the surface of the planet is huge. And so the signal we're pulling out is 10 to the fourth smaller than that background signal. And so there's a lot that needs to come in the ways of noise and accuracy to actually get that fine of a signal. So those are the two, so that's a major consideration too. But I mean, we are always interested, and it would be really cool to have more, data streams coming in, because then we could get down to even smaller spatial scales. So we could really start to look at what's happening here when things get really dynamic, like during storms, and we see these currents kind of going into these very weird filamentary shapes and doing very strange things. We could actually get a much better handle of that. And so not only then understand, the response of the magnetosphere and where that's coming from better, but also then how that's being imparted down the ionosphere and driving dynamics there, which is still kind of a big question, that interface region. So short answer is yes, actually. Yeah.
Awesome. Thank you so much. Yeah, great. And that was a great question. Thank you so much, Colton. And he said, thank you. So it sounds like it was a great answer. Thank you. So another question for me, because I'm always interested in people's past to where they are today. So Sarah, as long as we've got you here, we'll start this with you first. What was your favorite course that you took as an undergraduate, and which was the course that ended up being the most useful to you, because they might be different or they might be the same?
Yeah. Oh gosh, I haven't thought about this a lot. My favorite, I think, was trying to decide if I think it was a biology course, because we had to go out and do things. It was definitely not the most useful for what I do now, but it was the most interesting as far as, being in class versus we'd go out to the swamplands to count birds, or go to like one part of this like little inlet by one of the beaches to like grab like shellfish and things. And I helped a friend catch these weird little sharks at night one time. So that was I think that was the most interesting. The most useful, I will say, nothing beats a good E&M course. So if you have a solid E&M course, that will help you so much.
And what does that stand for?
Electrodynamics, or electricity and magnetism. And then actually really great mathematical physics courses too. So I think some of the most useful were actually like fundamental physics, like classical and D&M, and then some of the higher level math classes, just to help in the way that we need to approach and think about problems, and actually start from a very fundamental level in doing so. But
what about you? Thank you, Sarah. What about you, Anthony? Same question for you.
Yeah, I can definitely agree with E&M being one of the most important classes. That, and for me, computational physics was really great, because I had programming background, but being able to actually understand how you can use that to solve physics problems was super helpful and really cool. It's going to sound kind of weird. One of my favorite classes was actually quantum mechanics, and not because of the material, but because of the teacher. He did a really good job teaching it. He'd teach for the first like 50 minutes of class, and then send everyone up to the whiteboards and groups to do problems. He was super nice, but he felt really intimidating. So there was, when you got his like approval, it was really great. You felt very accomplished, but that made learning the subject much more enjoyable, and actually a good experience in the end.
That's great. Yeah, sometimes the teacher makes all the difference, for sure. Well, we have another really good question in the chat for each of you. We'll start with Dr. Sarah Vines. When did each of you first become aware of space science as a field of study?
I think for me, it kind of loosely, nebulously entered my awareness actually while I was in high school, and in a roundabout fashion. I had a teacher who was trying to be a civilian astronaut, and he didn't make it. He got part of the way through the process, and then would come back and tell us about it. And then I don't think he ever did eventually make it all the way through. But I think it was just even through him of being aware of these things and these different avenues. And so I think, yeah, I want to say around then, as far as like the avenue of space physics or heliophysics that I'm in now, that actually was probably my senior year of undergrad. I finally had an elective course in geophysics. And then so that kind of let me down. Like when I did see like flyers and for these SWIRI space physics program, I was like, okay, that was kind of that evolution. It was quite late, actually, to think about it.
That's okay. I mean, everyone has a different path, right? That's why we like to talk about these things. What about you, Anthony? When did you first become aware of space science as a field of study?
Yeah, so I always knew space in terms of like space exploration, like astronauts and NASA and all that. But it wasn't really until I joined Students for Exploration and Development of Space, which does have a large like industry aspect to it, engineering side. But some of the universities that are part of that organization were very physics-based, and I sort of found out about space physics through that. And then I sort of knew from there that that's kind of what I wanted to pursue in graduate school. So and then from there, it was kind of just a lot of browsing around and learning more about different programs I could apply to. And then I ended up at Rice.
Awesome, great. Let's see. Well, I had a question for Sarah for your work. It says in your bio that, part of the reason that we're interested in being able to predict space weather is because of the hazardous effects of space weather. So maybe if you could, really quick go through what some of those hazardous effects are and why we should care about them.
Sure, yeah. So once you leave what's known as low Earth orbit, so up, 400 to 1,000 kilometers in altitude. Once you leave there, a lot of the space weather effects really come down to energetic particles that are produced from the sun. So from explosive events in the sun and solar winds like coronal mass ejections and these shock regions that can form in interplanetary space. Basically, they accelerate particles to very high energies, and those particles can do a lot of damage when it comes to if it actually hits spacecraft. We have these things that are single event upsets or these weird discharge things that have been known to mess up instruments. And also, really importantly, radiation. So radiation hazard is a major concern as far as for any, human exploration out there. So as you get kind of down towards the surface of the Earth, so you still have these kind of radiation hazards, but then what happens when you get all these dynamics and currents is that you can actually get these very intense localized currents induced in the ground. And that can, everyone likes to bring up this like past thing about, disrupting power systems, blowing up transformers. That would have been back in like the 80s. So thankfully now we've mitigated against it, but these ground induced currents are very intense. And they are very hard to predict where they're going to occur. And they do cause some disruptions. Other things include changes to basically what's happening in the atmosphere, which affects satellite drag. Things that can actually affect GPS signals. So you can actually lose your GPS signals. And that has been actually a problem, especially if there's certain kinds of operations that require very fine, accurate knowledge of GPS and positioning. Otherwise, bad things can happen and a lot of people can get hurt. So, there's a myriad of those kinds of things. And actually over the polar cap region, you can have this enhanced dose of radiation just because you're basically at this portion where, you're a little bit more open to incoming particles from the magnetosphere and solar wind directly. So there's actually times when, basically they can divert flights from these regions to limit the amount of highly energetic particles you're exposed to. Oh, and things like how these things interact with ozone in the atmosphere, for instance. There's actually a cycle of reactions that can change what's happening at parts of the atmosphere that can have impacts down the road. So I'm trying to think, is there anything else? I think those are the main ones that come to mind as far
Have
as
you
some of the different
mentioned
hazards.
astronauts in space?
Yeah,
Yeah.
that's a bit, that's actually, yeah, the big one. We, don't want people to die in space.
Anthony, do you want to talk about that a little bit more, the human explorer aspect of it?
Yeah, sure. So, so yeah, inside Earth's magnetic field, humans are actually relatively protected from it, but radiation is definitely a concern when you're talking about going to Mars and stuff. And so for that entire trip, you don't have this large-scale magnetic field around you. And so one of the big questions right now for going to Mars is how affected is the crew going to be on their way there? And then also, Mars doesn't have much of a magnetic field on its own. So the question is, how are they going to protect themselves against it once they're there? And so that's an active area of research as well.
And certainly being able to predict, if there was a way that astronauts could take shelter from something, being able to predict when and where it will be would help a lot with that. So thank you.
Yeah.
Okay, so Danny Stover has a question he wanted to ask himself. So I think he can he unmute himself, Slava, or do you need to unmute him?
Yeah, I'm able to unmute. Can you guys hear me?
Okay, yes, we can. Go ahead, ask your question. Thank you.
Yeah, I'm a Virginia Tech undergraduate, so nice to meet you guys. Thanks, Kevin Stern, for setting out the link. But anyways, I've always wondered, why is Earth's magnetic field shaped as it is? Like, why does it have like such a long tail? Why does it, dip down at the poles? And I guess, as someone who doesn't really study magnetic fields, this is something that you guys may think is obvious, but not obvious to me. So
Yeah, I can go ahead and start with that. So I know that, and that's actually a really good question, right? So as you think, it's largely dipolar, right? So a normal dipole would have this nice, very symmetric structure. So the reason it's actually blunted on one end, so on the day side of the Earth, and then extends into the long tail on the night side of the Earth, has to do with the solar wind. So the solar wind is, in the interplanetary magnetic field, are emanating outwards from the sun constantly at this very large speed. So typical speed of 400 kilometers per second, which I know that there's equivalencies for, but I can never think of them. But it's fast enough, basically, that you have this thing, it's basically dragging out the tail of the magnetosphere with it. And so it's like kind of blunting it on one side, dragging it out on the other. And so that's probably, I think, the main aspect for the shape of the magnetosphere. I think Anthony or Slava, do you want to add anything to that general description?
I can share that image I had early on, where this is an extreme example, of course, but what you can see is these lines being drawn through is a magnetic field of, this is the solar wind, and then it'll flow by the planet, and the field lines will be connected to the planet, and that sort of pulls the whole system back. You can see how they get curved in, and so that drives a lot of interaction, and then that stretches out the tail of it very much, pretty far. And also, I know space usually thought of as being very empty, but on these scales, even just a little bit of pressure turns out to interact quite a lot over these global scales. And so you can think of it a bit almost like as a rock in a river with the water flowing around the rock, except here the obstacle is the magnetic field, which it can sort of move back and forth based on the balance between the two pressures, but it's still an obstacle that you, but it's much more complex than that, but that's one way of looking at it.
That's great. Thank you so much. Well, this takes us, that was a great question to end on. It takes us right to 4:45. Thank you so much to our panelists for joining us today. Great discussion. Thank you so much to all of our participants, viewers who came and joined us today. And Slava, if you want to say any closing words, I'll go ahead and leave that up to you.
Yeah, so I thought it was great. There were some really great questions. I liked very much Danny's question. It was spot on. So you got it. Yeah, so we'll do it again in 3 weeks. I think we'll have 2 other wonderful panelists for you, and you should have the flyer that we sent around. It has my email. Feel free to email any questions back to us, and we'll be happy to help with getting you information about opportunities or whatever questions you might might have. And we'll be back in 3 weeks. Thank you so much, and thank you so much to panelists. It was great.
Yeah, thanks for having us.
Thanks,
Excellent. Thank you guys so
everyone.
much.
Thanks everyone for attending.
Bye.
Bye all.
Bye-bye.
Thank you.
Bye.